This skill module covers contaminant removal, gas dehydration at the core knowledge level. This section discusses why this topic is important. There are several reasons why gas must be dehydrated. Dry natural gas to meet sales or transportation specifications. Remove water to prevent corrosion in gas gathering systems, gas lift systems, and large diameter trunk lines that deliver gas from offshore platforms to onshore gas terminals or processing facilities. Remove water upstream of low-temperature gas processing facilities and LNG liquefaction plants to prevent freezing in the process. The three most commonly used gas dehydration processes are absorption. Water is removed by absorption into a liquid solvent with a high affinity for water. Glycols are the most commonly used absorbents. Condensation and inhibition. Water is removed by condensing it, usually with refrigeration, and inhibiting hydrate formation with an inhibitor, usually glycol or methanol. Adsorption. Water is removed by adsorption onto a solid desiccant. Common desiccants include molecular sieve, which is a zeolite, silica gel, or activated alumina. Understanding the most common process options for natural gas dehydration and their typical applications is helpful for individuals that are just becoming familiar with natural gas dehydration. In addition, understanding the limitations of a given dehydration technology is helpful in appreciating your facility's process operating performance constraints. Glycol dehydration is the most common process used to dehydrate natural gas. Understanding the process flow, the purpose of each piece of equipment, and the key performance parameters of these systems is an important first step in deepening your knowledge on how this technology works. Natural gas that contains acid gas components and aromatic hydrocarbons can result in emission issues at the TEG regenerator vent. H2S and aromatic compounds have regulatory emission limits, as hydrogen sulfide is toxic to humans and results in acid rain. Aromatic compounds range from being carcinogenic to strong respiratory irritants, thus the limit on the quantities of the compounds that can be safely vented. Carbon dioxide is co-absorbed as well, and at high inlet gas concentrations and high contactor operating pressures, this can result in corrosive, rich TEG that requires special metallurgy. One of the advantages of adsorption systems is that in addition to dehydrating natural gas to very low water contents, they can also remove other contaminants from a gas or liquid stream. Applications of adsorption systems in gas processing include the following: dehydration to less than 0.1 parts per million volume, deep NGL extraction, and LNG plants; simultaneous HCDP control and dehydration; simultaneous dehydration and sweetening of natural gas concentration of sulfur compounds less than approximately 100 parts per million; dehydration of gases containing hydrogen sulfide; trace sulfur, hydrogen sulfide, carbonyl sulfide, mercaptans, removal from LPG and natural gas streams; and dehydration of NGL streams. Adsorption dehydration is required for cryogenic gas plant and LNG facility operations. For these facilities, it is important to understand the factors that affect the equilibrium capacity of molecular sieve and explain the difference between new and aged capacity. Understanding the key performance parameters of a molecular sieve dehydration unit helps to maintain low water dew point specifications, prevents abnormal decay, and extends the life of the mole sieve bed. This skill module also describes the mole sieve regeneration process and discusses factors that affect its design and operation. This figure shows a simple dry desiccant system. The required regeneration gas flow required is a function of step time, the source of regeneration gas, and the type of adsorbent that is used. The disposition of the spent regeneration gas must also be decided, as additional processing may be required to remove water and/or other concentration peaks such as H2S. The heating cycle is most critical because if the bed is not adequately regenerated, it will not be able to meet the required water content, dew point, when the bed is brought back on to adsorption. The bed will experience premature water breakthrough as a result of incomplete regeneration. This skill module discusses the topics shown here. You may also be interested in these gas conditioning and processing principles skill modules.